was 80-2021 LWX. But this was a transient which was discovered from the ZTF survey, which I was talking about. So ZTF alert streams generally come with an ID. So the ID for this transient was ZTF, followed by the year it was discovered, so 20, and then followed by a 7-letter word, so ABRBEIE. And when we were monitoring this transient and investigating this, a graduate student in our group, Danielle Dickinson, she was like, that sounds like Barbie, and we all agreed to that name. And we decided to go with the name. Astronomers are allowed to have a little bit of fun, so we conclusively agreed we're going to call this Barbie. Now, what characteristics of this transient makes it stand out from all the other optical transients that we have seen so far? So if you look at the light curve on the left, this is the light curve from the ZTF survey. It has started, the first discovery was in 2020, but this light curve is still keeping on going. So it's a long duration transient, which has, in the observer frame, it's over 1,000 days right now, and it's currently evolving, still evolving. Now, things started getting really scary when we actually got a sense about the distance to this transient. So we have a system at Purdue where we filter through these transients and look for interesting ones. And this was initially tagged as a high priority interacting supernovae because of its rise time. And then it was triggered for follow-up. But once we got a sense of the distance of this transients, then things started really becoming really scary, because we were able to calculate the luminosity distance and absolute magnitude of this transient, able to get a sense of the total luminosity of the transient. And it is very, very luminous. So it's ultra luminous. And here is a comparison of how it compares to the different optical transients that we have so far. So here I'm showing you the different classes of supernovae. So even within supernovae, there are superluminous supernovae that are orders of magnitude brighter than the normal supernovae. And Scary Barbie is really scary and whoppingly at an absolute magnitude of minus 25.7, right? So this is really, when you translate this to the luminosities, which I'll in a second, but it translates to luminosities which are orders of magnitude than a normal type of supernovae that we see. And the time scales are also really crazy. So I'm translating it from the observer frame to the rest frame now. So the rest frame, it's approximately at a redshift of 1, so it's half the time. So it has a rise time of over 100 days, and it is still keeping, and as I'm talking, and this frontier series now, this transient is still continuously evolving. Right, okay, oops, all right. So once it's we started following it up in multiple bands, and we start as well as in other parts of electromagnetic spectrum. So initial spectroscopic follow-up is where we got a sense of the distance of the distance to the transient. So here I'm showing the ultraviolet and the optical spectrum of the transient taken over multiple epochs. And I have to say it upfront that we were not able to capture this at the time of peak. So this transient was discovered because of its long duration later after the peak in our automated system where we prioritize transients. So we were unfortunately not able to capture the peak or spectroscopic follow-up at the peak of the transient. But we were able to later follow it up at multiple epochs. And on the left, you're seeing different spectral observations at different epochs. And initially, it has a slope, a bluer slope, but later it just becomes a very, very flat spectrum. And as you can see, there is not much evolution within these epochs. So that's really one thing that we need to keep in mind. Now, what does a spectra look like itself? So we see prominent Balmer lines, so H alpha, H beta. So there's no H alpha here, but we do have observations of H alpha, which is another talk. But in the paper, we show these Balmer lines, and then there are different strong semi-forbidden lines. So, and if you decide, if you take the profile of the H beta itself, and then if you look at the, if you fit Laurentian and Gaussian state, you see that there is a strong narrow core about 300 km per second, and then you do have, oops, you do have these broad wings, which are almost about 3,000 kilometers per second. So initially, just putting it out there that when there's a system where this was classified initially, and the spectra was tagged to be an AGN spectra, and there are other reasons why I would argue against that it's an AGN. Just going back to the slide where you see the comparison of the light curves, I have also shown why it is very different from an AGN here. The gray line, the gray points that you see, those are of an AGN, and it is very stochastic and random, as very starkly different from Barbie, which is very smoothly evolving. All right. Now, here I'm comparing the spectra, which is the highest quality spectra of Barbie with respect to other optical transients. So here, the Assassin 17JC is an ambiguous nuclear transient. There is these composite QSO quadrilateral objects. And other comparisons are with interacting supernovae, which is 10JL, and then there is a TD, which is compared to, but these are not compared at the similar times. That's something that needs to be kept in mind. But one thing that marginally differentiates Barbie from, say, for a quasi-stellar object is the missing oxygen doublet. So initially, this was classified to be an AGN spectra. I said this was a E-Pesto group which classified it as to be an AGN spectra, but the starking difference was that we were not seeing, even in our highest quality spectra, the very dominant line in AGN, typical AGN as well as QSO spectra, which is the oxygen doublet lines. It's different from interacting supernova or other normal TDEs because normal TDEs tend to have much more broader, not these narrow line cores. And then the interacting supernovae also tend to have other more metal lines, which are absent in the spectra of Barbie. All right, now, initial guesses. So we started prioritizing this transient as interacting supernovae, but as and when we were looking at the energetics as well as the luminosity of this transient, it did not make sense to, the supernova explosion models were not unable to produce these luminosities as well as energies. So the initial guess, what we had was there is a supermassive black hole at play, which might be efficiently converting matter into energy. So the way we approached this was we tried to model it with a tidal disruption event. So when a star gets very close enough to a black hole, it gets tidally disrupted, and then these are called as tidal disruption events, and they are commonly seen as tidal flares too in active galactic nuclei. But in a moment, I'll show you why it's not the AGN, or there is why we are against that. So the light curve modeling of the scary Barbie with a TDE, because of its extreme characteristics, also gave extreme parameters, which is not common in the TDE regime. So we do not conclusively say that this is a TDE, but we do think that it is a hypothesis that this could be an extreme TDE candidate, but it's not confirmed yet. So these extreme luminosities tend to show that it might be a very supermassive black hole which is at play, which is tidally disrupting a puffy star, which is about a solar mass, which is about 14 solar masses. Now, we also have other observations. So in X-ray, there were detections in Swift, detections with Swift, and it is consistent with observations, X-ray observations with late TDEs too. So it was detected in soft band, but there were no radio detections. So we searched in the very large array sky survey, and then we were not able to find any radio detections. Now, if you look at the plots, it has initially a blue color, and it is consistently becoming redder and redder. It is falling off with T to the power minus 5/3 power law, which is another reason why we tend to think that it could be some kind of accretion event, which is initiated by a tidal disruption event. But relatively, the temperature of this transient, the evolution or the temperature evolution of this transient is not consistent with TDs. It's much more cooler, but TDs tend to be much more hotter. Now, so as to say, long story short, this is something really, there is some system which is powering this this luminosity and energetics, and we do think that it is a supermassive black hole at play. But there is a weirder part which makes it completely intriguing. So, and Ataya, this is my last slide. So I think I'm on time though. All right. So yeah, the reason, one of the main conclusions that we thought that this is not an AGN is that where is the G in the AGN? So this is the a field. This is the detection, as well as these are the fields of 80, 20, 21 LWX. So in the leftmost image, you see 80, 20, 21 LWX detection and the field of it. So the green circles are from Gaia. So those are cataloged stars. And if you zoom in, and here is the middle panel shows a field of 80, 20, 21X before its detection itself. So we were looking at pan-stars images to see if we were able to find any host galaxy for this particular transient. So if there was a supermassive black hole at play, there should be some underlying host which is associated with the supermassive black hole. We do not find any. That's really puzzling. And here is a zoom in location of the same zoom in part of the middle panel. So that 3 dots of red might be something, but it's mostly my stretching. I did the stretching, so it could be a part of the color image and the stretching too. So I don't believe it completely yet. So, but hey, there could be some estimates of the host galaxy, right? You could do it with the Eddington limits, as well as you can find a mass of the black hole for the Eddington from the Eddington luminosity, then translate it to underlying host mass using scaling relations. We did that. So what we found was there is a possibility of a host galaxy which is about 10 to the power 10 solar mass, and that's not something which is very small. It is like our own Milky Way galaxy, like 10 to the power 10 solar masses should be seen, right? But we do not see that in the pan-stars images yet. So long story short, this is a really weird transient. It is very luminous. I could definitely say that this is one of the most energetic and luminous transient, which we have a luminous optical transient, which we have ever observed. The story is not complete yet. We need more observations, especially to see if there is any underlying host galaxy for this transient, because there was a similar paper which came in around the same time, which told that it might be a disruption of a massive molecular cloud. But still, for the supermassive black hole to exist, they had similar estimates of the supermassive black hole, which is like 10 to the power 8, and it's like it needs to be either highly spinning, or it's just there needs to be a host galaxy there. That's our hypothesis so far. So more observations are needed to conclusively test these interpretations that this is a TDE. So stay tuned. There are more things to come in the way. So I'll just stop there. And if you need the data for this transient, you can scan the QR code and it's readily available. Thank you. I think, yeah, that's it. Thank you for listening, and then I'll be happy to answer a few questions.
Thanks so much, Bhagya. We can take questions. Please feel free to unmute yourself or even write it in the chat.
Oops.
We have a hand up. So Eric Perlman?
Yeah. I had a question, and actually this last slide, as well as the light curve, really kind of encapsulates what I want to ask about. It seems to me that the light curve, the overall light curve, looks a lot more like a supernova than like a TDE. And one of my grad students is working on using supernovae as signposts to identify faint galaxies. And, we've identified some quite faint galaxies this way, and that might be much more consistent with the lack of, or apparent lack of, a host galaxy.
I can comment on that. So traditionally, my training was in supernova, though. So initially, this was tagged to be a high priority interacting supernova, though. But having those luminosities, or like 2 orders of magnitude of energetics with neutrino explosions, is really hard to achieve. So that's the reason why and even if you want an interacting supernovae to have those energetics, you would at least need to shed out like more than 100 solar masses of material out, which is, that is not usually or typically seen. So it is right that if it was not a supermassive black hole, okay, the host galaxy might not be, and then might not be an issue at all, because it would just it would be very dwarf, and it is not detected in the initial pan-stars images. But infrared observations really are the key. So if there is something really dust obscured or very dwarf, Hubble or James Webb would be definitely able to resolve the structure underlying. Well, if it was something which was the t to the power minus 5/3, the power law, that is also like starting, right? Like, so it's very, very, very smooth. It's just constantly evolving, and it's not even like changing. So that's very different compared to like nickel powered explosion light curves. So those are my initial thoughts about that. So it really requires like extremes, or even with supernova models, to just explode those. So those explosions like need real consideration. So, or if there was no underlying host galaxy detected, then we would have to seriously go back and revisit these explosion models and make tweaks, I would say, to explain this transient. Also with the spectroscopy, though, like it's just basically Balmer lines. You're not seeing much more any structure, or like you are seeing semi-forbidden lines, though, but like a general elements which are typically seen, like it's not, I would think, not seen.
Okay, thanks.
And it's not evolving at all. So that's the other thing. Like over epochs, it's just fading, though, but it's not like there is no evolution of the lines itself. So that's the thing that to be considered.
Okay, thank you.
Thanks so
Thanks
much,
for the question.
Bhagya. Thank
I'll
you.
stop sharing.
Yes, thank you. So we should move on to the next talk. There was another question in the chat, but maybe Bhagya, you can look at that and address it in the chat. It was about whether there was any Fermi emission detected. All right, our next speaker is Sanskriti Das from Stanford University, and she will tell us about the detection of turbulence in the hot CGM of the Milky Way.
Hello, everyone. I'm just assuming you can hear me and see my slides. So I will start. Hello, I am a KIPAC postdoctoral fellow at Stanford University. I work on the hot diffuse circumgalactic medium of Milky Way and also on external galaxies. But today I'm going to focus on one of our recent discoveries of constraining turbulence in the hot CGM of the Milky Way. Now, as CGM is a comparatively new field, I'll start with the picture that is used in pretty much all CGM talks, and I'll define what CGM is and why we need to study it. So circumgalactic medium, or CGM, is basically all the gas that is outside the interstellar medium, but within the virial radius of a galaxy. So for a Milky Way-like galaxy, it is the gas that's outside roughly 30 kiloparsec, but within 300 kiloparsec. And one of the main reasons we need to study CGM is because it might host all the baryons and metals that are missing from the stars and ISM. If galaxies are baryon sufficient, we do not find all the baryons within the galaxy disks. And that implies there might be a lot of mass, almost as much mass in the disk as in the CGM. And also, we do not find all the metals in the ISM and the stars that we expect the stars to form, which means the stellar feedback and or AGN feedback might have expelled a lot of metals from the disk to the halo. So CGM, in principle, plays a huge role in the evolution of a galaxy. So we need to study them. And it is a rich multi-phase structure. Its density and temperature both spans more than 3 orders of magnitude range. But the most massive and volume-filling phase of the CGM is above million Kelvin hot. So we can observe that in X-ray. And this hot CGM has primarily two components. One is the incoming gas that comes from the intergalactic medium and is shock heated during gravitational collapse. So for any galaxy, given the halo mass, we know what the virial temperature is. That's what the temperature of this hot CGM is. But also there are galactic outflows, which are generally hotter and denser. And the mix of these two phases decides what the detailed properties of the hot CGM is going to be. And while I explain this, you might have already guessed why the hot CGM would be turbulent, because both during structure formation and outflows, the density and temperatures are perturbed depending on the strength of the outflows and what the shock heating is. Here in the simulation, you can see in the left, the density, in the middle, the temperature, and the right, non-thermal broadening. So in general, CGM is often assumed to be a spherically symmetric or cylindrically symmetric density and temperature model. But both during structure formation and due to galactic outflows, these distributions are perturbed. So we see a lot of local fluctuations in the density and temperature, and we can measure that from X-ray observations. Now, turbulence affects both heating, cooling, and mixing in the CGM, so it is paramount to the multiphase structure of the CGM. And in the subvirial phases, that are the cooler phases observed in UV, turbulence has been studied in huge detail. But as the hot CGM is much more difficult to detect, for the last 2 decades, we have been mostly focusing on detecting the CGM and constraining its density and temperature. And this is the first time we have tried to constrain the turbulence in the CGM. And Milky Way is right now the only galaxy where we know about the CGM in detail. So I'm just going to focus on that. Now, CGM can be observed both in X-ray emission and X-ray absorption, but as X-ray emission is proportional to density square, it is biased toward denser gas, which is most likely to be closer to the disk. But if we want to probe the low density gas extended out to the virial radius, it is better to observe in absorption because it is proportional to density. So it is not biased toward only the denser gas. Now for this, we look toward extragalactic QSO sightlines, which is basically blazars and warm absorbers. But since we are sitting in the disk, we always focus on B greater than 0, galactic latitude greater than 20, so that our path length barely passes through the ISM and mostly probes the CGM. And we focus on Z equal to 0 lines because we are looking at Milky Way. And since the lines are very weak, these lines are basically unresolved narrow lines, unlike, for example, the broad and strong warm absorbers. And in the temperature, we are expecting oxygen is the most abundant metal. So we focus on the highest ionization fractions of oxygen in that temperature, which is oxygen 7 and oxygen 8. Now for this study, we need both oxygen 7K alpha and beta, the strongest 2 lines. I will just explain in a moment why we need both of them. And we also need oxygen 8K alpha. Again, I'm going to explain why we need that as well. So here I'll be presenting roughly 72 sightlines where we have measured this. In all of the sightlines, we calculate the equivalent width of these 3 lines, and then we combine the K alpha and K beta lines of oxygen 7 to obtain the saturation corrected column density of oxygen 7. Often the saturation corrected column density is larger than what you expect from the linear part of the curve of growth. So we have to be careful about combining these K alpha and K beta lines. And once we have that, we can use the column density ratio of oxygen 8 and oxygen 7 to obtain the best fit temperature as well as the ionization fraction of oxygen 7 at that temperature. Now CGM is roughly collisionally ionized. That makes things easier. It is far away from the local ionization sources, so it is unlikely to be locally photoionized. And also its density is high enough to be not photoionized by the cosmic photoionizing background. So unlike the local ISM or the intergalactic medium, CGM sits somewhere in between where it is collisionally ionized. So we assume the ionization fractions in collisional ionization equilibrium and obtain the temperature for each of the sightlines. And once we have the ionization fraction of oxygen 7, we can calculate the total column density of oxygen, and assuming a constant metallicity of 0.3 solar, we can obtain the hydrogen column density. And as this gas is completely ionized, we can also obtain the dispersion measure, which is the line of sight integration of the total free electron density along the line of sight. So in the left, I'm showing a figure we published in 2021, where we show the log distribution of dispersion measure, which spans 3 orders of magnitude and is skewed towards the right, which kind of already shows you that it is not just a spherically symmetric distribution of density. And here the mean is larger by a factor of 3 than the median, which also shows why the skew matters. And in this new paper, we are trying to focus on the detailed structure of this dispersion measure distribution, where the first thing we study is the clumpiness, which is significantly greater than 1, showing local density fluctuation. And to constrain it further, we consider a correlation function of the density fluctuation. This has been already used to study the turbulence in the intergalactic medium. So we use the same function. Here, the two main things to focus on are LT, which is the correlation length scale, or the length scale of driving turbulence. So if there are large scale turbulence, we expect this term to be as large as the length scale of the CGM. Otherwise, it would be pretty small and maybe a negligible fraction of the CGM length scale. The other term is the M. It constrains how strongly the turbulence depends on the angular scale. In the ISM, for example, we know it roughly follows the Kolmogorov type, but in the CGM, we do not know. So we try to constrain that. And for this given density fluctuation, we can obtain the structure function of dispersion measure. And in the left-hand side, what we get is the empirical value. So we have dispersion measure along every sight line. From that, we can get the structure function. And for 72 sight lines, we have roughly the combination of 2,500 sight lines, which gives basically a lot of data in the left-hand side. And in the right-hand side, what we have is in the small angular separation, the structure function grows with the angular separation. And when the angular separation is large enough, the density fluctuation is not correlated anymore, and the structure function saturates at a given point. So we primarily have 3 variables. One is again M, that tells you how the turbulence is growing with the angular separation. And this ratio is the critical angular separation that is proportional to the driving scale of turbulence beyond which the correlation function saturates. And the other one is the average density fluctuation, which tells you the magnitude of density fluctuation. Is it too large, small, etc.? And now I'm going to share the 3 main results. The first one is the critical, angle or angular separation, which tells you the driving scale of turbulence, which is roughly 25 degree to 40 degree, which is actually huge. And that tells us that the outer scale of density fluctuation is a large fraction of the virial radius. So in the CGM, we are actually seeing large scale density fluctuation, which kind of refutes the previous spherically symmetric density distribution assumed in pretty much most of the analysis. And the second result is, which we get from the saturated value here, that tells us the characteristic value of turbulent dispersion measure. And from that, we can obtain the clumpiness again. And this is again consistent with the previous empirical turbulence we got. And that is again significantly larger than 1, showing that the hot CGM is quite clumpy, which is another reason we can't use the smooth and isotropic spherically symmetric density distributions. And the third result is M, or in this case, we are using M plus 1 because that's kind of the convention, which is significantly greater than not only 0, but also greater than 5/3. 5/3 is the value for Kolmogorov-like turbulence, which basically tells you the turbulence of a spherically symmetric distribution, and it is often used in ISM or even in clusters in larger scales. But as we see M is larger than 0, that tells us there is indeed scale-dependent turbulence. But it also tells that since it is greater than 5/3, the turbulent energy is more in the larger scale than expected. And surprisingly, this is exactly opposite to what we see in the interstellar medium, where it is less than 5/3. So that tells more turbulent energy in the smaller scale. But we are seeing an inversion from ISM to CGM, where large scale turbulence is having more energy than small scales. And now we are trying to compare with different simulations, both fire simulations and idealized simulations, to see if we can reproduce these observed structure function. So here, one of the models is that we start with spherically symmetric density model, because that's what people assume and has been doing that for maybe last 2 decades. But then we include kind of inject feedback at the center and let it travel through the whole CGM. And at different times, we try to see how the structure function evolves. As you can see, if I can go back by one slide, you can see that roughly speaking, the structure function first grows with angle and then saturates, and we see the same thing roughly in the simulations as well. So now we are fine-tuning things to get the exact values consistent with our data, and once we have that, we'll be publishing it. So it's roughly in the advanced draft stage. So having said that, I will now summarize my results. CGM in general is important to understand the properties of the galaxy evolution. Constraining galaxy evolution and turbulence is one of the main constraints. So for last 2 decades, people have been assuming spherically symmetric density distribution of the CGM of Milky Way, but we kind of refute that with our turbulence studies, showing that the CGM is quite clumpy, and there is large-scale turbulence in the hot CGM, at least in Milky Way. And we find that not only it is scale dependent, it is stronger than the isotropic turbulence, and it is opposite to ISM. So we are yet to study, understand why that is happening. And we need more and more grating observations along more sightlines at smaller angular separation, as well as more precise measurements to get a better constraint on the turbulence, first in Milky Way and eventually in external galaxies. So right now, Chandra and XMM grating data would be very useful. But eventually, if ARCAS is hopefully, approved, then that would be great. So having said that, I would stop, and thanks everyone for listening. I'll take questions.
Thank you so much. Any questions? Please unmute yourself or raise your hand or write it in the chat.
So
That was a great, sorry. That was a great talk. Thank you. I did want to ask, so are there any sort of initial thoughts on what could be causing this inversion in the scale of turbulence, that it's stronger at the larger scales? What are some possibilities?
So one of the simplest assumption is that the feedback is much stronger in Milky Way-like galaxies than we think. And by stronger, I mean, one, the mass loading factor must be much larger than what we expect. And 2, there might be more, stellar feedback than just nuclear feedback. The thing about stellar feedback is that it is disk-wide. It is not just concentrated in the inner galaxy. And if something is disk-wide and has larger opening angle, it is perturbing things at different radius and at different azimuths. So it is not kind of centrally controlled, and that can perturb both density and temperature strongly, at least in the local region, than only a nuclear feedback. And secondly, we think that the thermal output from feedbacks are probably much stronger than we think. That's why we are seeing so much fluctuation even in the hot phase. Because if there is just a lot of mass from the outflow, but most of it cools down, we won't see it in the hot phase. It would just be in the cooler phases. That is already constrained. So overall, yeah, I think the mass loading factor and high thermal energy of feedback are one of our simplest assumptions. And we just had a meeting last week to get these results from simulations. But now we are also exploring the effect of cosmic ray and magnetic fields to see if non-thermal components are also affecting the density fluctuations as well.
Thank you so much. Any other questions? All right, we will move on to our next speaker, Alessandro Peca from the University of Miami, and we will hear about the evolution of high luminosity and obscured AGN in the Stripe 82 field.
Can you see it and can you hear me?
Yes,
Yes.
looks
Okay.
great.
Yeah. Okay. Thank you for having me here today. My name is Alessandro Peca. I'm a last year graduate student at University of Miami, and my advisor is Nico Cappelluti. Today I talk about our work on Striped-2X on high obscured AGNs and luminosity functions in Striped-2X, plus I'll give you some recent updates. So, wait, okay, it's working. Okay, so I'm going to introduce why we decided to do this work. So why we decided to study obscured AGN and why we think that we still have a problem with them. And to answer the question that we have on obscured AGN, I'm going to propose two different solutions. One is using large area X-ray surveys, and the other one is using the AGN database, which is a very beautiful database that we are building here in Miami. So why do we have a problem with obscured AGNs? Well, when we talk about obscured AGNs, we need to start from the cosmic X-ray background. So here you can see the cosmic X-ray background. The orange points are the detected points, and the black and gray lines here are the best fit model. So we believe that the cosmic X-ray background is produced by unresolved AGNs. So what we can do with the X-ray background is to try to reproduce it using AGN population synthesis models, which basically means try to fit the overall cosmic X-ray background using different populations of obscured AGNs. And here you can see in this plot that except for this green line here, which is the contribution coming from the host galaxies, all the other contributions, all the other lines are the contributions from different obscured AGN population. And in particular, I want you to focus on the red line here, which shows you the contribution of Compton-Tick AGNs, which are AGNs with line of sight column densities in log scale larger than 24. So what we can do with the models is try to infer the number density of AGNs. But the point is that, do we see them in the observations? And the answer is not very well. So to show you the problem here, I'm just proposing you one example. So this is a work by Torres Alba 21 and later updated by Sengupta 23. And the authors here measured the fraction of Compton-Tick AGNs in the 100-month Swiftbat catalog, which is almost biased against obscuration. So the authors found up to redshift 0.05, an obscured fraction, which is around 8%. However, when you take population synthesis models, the predicted intrinsic fraction should be between 20 and 50%. So for example, here, if you take the ANANA 19 model and you consider all the observational limits and biases that you have in this catalog, you get a prediction of Compton-Tick AGNs, which is around 27 and 38%. So there is a huge gap between what is observed and what is predicted. And even if you take another model like the WEDA 14, which predicts less Compton-Tick sources, you kind of get close to this 8%, but you never match. So we have a discrepancy. In addition to that, we know that obscuration increases as a function of redshift. And of course, heavily obscured AGN are faint. So at high redshift, they are even more difficult to detect. This is to say that this discrepancy between observations and model is expected to increase at high redshift. And the question is, how can we solve it? And is this the only issue? So to solve this question, we propose first solution A. So we try to use large area X-ray surveys. So here on the left, you can see the sensitivity area plot of some of the most famous X-ray surveys. And basically, this is telling you that if you want to get very faint sources, you need to sample small areas. And the reason is that we don't have a perfect telescope, so we cannot at the same time go deep and observe large areas of the universe. So if you want to observe large volume of the universe, you need large area surveys like XMM-XXL or STRIPE-82X or other surveys. But using these surveys, you cannot go very deep. However, if you take whatever luminosity function, like this one taken as an example here, you can see that there is a drop at high luminosity, meaning that if you want to sample high luminosity AGNs, you need to sample large volume of the universe because those objects are rare. In addition to that, high luminosity and high NH AGN seem to be in a very important key phase of supermassive black hole evolution, according to theoretical models. This is why it is extremely important to sample large volume of universe to get a number large enough of high luminosity AGNs. So we decided to use the STRIPE-82X survey, which is a large area survey of XMM and Chandra data over more than 31 square degrees, in which we also have a high redshift completeness and we have a huge multiband coverage. In addition to that, we have numbers because we have more than 6,000 unique X-ray sources, plus 1,500 hard band detected sources, which is always good when you are looking for obscuration. So this is a sketch of what we did. We started from the La Massa 16 master catalog. We made some redshift and X-ray spectral quality cuts, meaning that we used only sources with spectroscopic redshift or high quality photometric redshift. And we made extensive use of MCMC simulations to get the minimum number of X-ray photons for which you can get a meaningful fit. After these cuts, we got a final sample of around 3,000 AGNs. And we did our X-ray spectral analysis. So here you can see one of our results. On the y-axis, you can see the intrinsic X-ray luminosity as a function of redshift. You can appreciate, so our points are the yellow ones, you can appreciate how well we sampled the high luminosity region of this plot and how we share the area with other large X-ray surveys like XMM-XXL. However, since for some reason I'm obsessed by obscuration, I was wondering how many faint and obscured AGN we are missing because the sensitivity of our survey. And to answer this question, I mean, it's possible to answer this question by using simulations. So this is what we did. This is a cartoon of what we did. So we simulated a lot of fake spectra as a function of redshift, luminosity, and absorption. And by including observational limits and biases, we got something like this. So here, this three-dimensional histogram is showing you as a function of NH and redshift, the percentage of sources that you can get in STRIPE-82X. So 1 minus this number is the percentage of sources that you are losing in STRIPE-82X because the survey is not deep enough. So this is our percentages. So you can consider them as corrections. So we can correct our observed distributions. In this case, just as an example, here you have NH, LX, and photon index gamma. And without assuming any luminosity function, you can get intrinsic distributions. And when I say intrinsic, I mean that we could analyze both the observed AGNs, but also those that we missed in our observations. This is one of our results. So here you can see the fraction of obscured AGN as a function of redshift for 3 different luminosity beams. And you can clearly see that at all these luminosities, the fraction of obscured AGN clearly increases with redshift, at least up to redshift 4. And in particular, we are proud about this green plot on the right because it's showing you that we were able to put very solid observational constraints in this high luminosity regime. And all these points are fitted, and if you want the models, and if you want example on how to use these models, just go on our paper and please use them. But then we did more. Now, I don't have to go into the details, but since we had intrinsic numbers, we computed our X-ray luminosity function. And in particular, we were able to distinguish between obscured and unobscured X-ray luminosity functions. Also, we computed up to redshift 4. Also, we computed the black hole accretion density evolution, and we also made some prediction on the Compton-Tick fraction that we should see in this survey. But now I want to switch on some updates. So how can we improve current results? So a while ago, we won this Chandra archival proposal. And basically what I showed you is all the data XMM and Chandra in Strip-2X from the beginning of XMM and Chandra to 2016. But from 2016 to today, we found that there are many more XMM and Chandra new observations. So we included them and we updated our catalogs. Right now we have more than 5 times the previous X-ray sources. In some overlapping regions, we are almost 2 times deeper, and we are now reaching a total area of around 55 square degrees. So our expectation is to extend previous results at redshift larger than 4, at luminosities in log scale larger than 46, and also we aim to get many Compton-Tick sources in order to constrain better the Compton-Tick fraction of sources as a function of redshift. So this is just some preliminary results. So we have more than 23K sources, and just plotting the fluxes, you can see here compared to the old Strip-2X how many more sources that we have and how deep we can go considering the fluxes. We already did the multi-band counterpart matching, and we have a completeness of around 92%. And we did the matching with Lyra, which is a maximum likelihood estimator that I wrote, which includes Bayesian statistics and is able to automatically detect priors on magnitude, density, and completeness. So we are doing right now the spectral analysis, so we hope to publish soon. And basically, we are going to increase the previous results. But now I'm proposing you very quickly in the solution B, which is about the AGN database. So I showed you how large X-ray surveys can improve our current understanding of obscured AGNs. However, we wanted to go bigger than that. So what about using all the AGNs that are available in the literature? So the AGN database, or AGNDB, is the repository of all the discovered AGNs at all the wavelengths, at all the redshifts. And it includes information on redshift, classification, photometry, images, spectral energy distributions, and in the future also we will have spectroscopy. So how we build such a database? Well, first of all, we store together all the catalogs of classified AGN available in the literature. And then we wrote our pipeline that is able to unify all the units to the standard CZS system, is able to deal with all the catalog formats, is automatically merge overlapping catalogs. And the nicest thing is that we can ingest new catalogs almost automatically. The final output of our pipeline is a single, unique, huge master catalog. And we are also developing a website in which you can make queries, download the results, and have access to images, SCDs, and in the future also spectra. So this is a preview of what we have. So this is a density plot. So here you can see the AGN that we have discovered so far in the universe. And so far we have around 7.5 million of unique AGNs here. And the fact that you see geometrical shape, for example, you can recognize the SDSS shape, is just telling you that in some region of the universe, we have more observations, and so we discovered more AGNs. So very quickly, this is just some numbers that we have. We have a high redshift completeness, 66 magnitude and flux bands, almost 1 million X-ray sources, and several millions of near-infrared, near-infrared, optical, far-infrared, and radio information. So why the AGN database? Well, we are currently performing the X-ray spectral analysis on the entire catalog. So again, this may be the best way to improve our current results, since we decided to answer the question about obscuration in AGNs using large numbers. However, AGNDB is not only about obscuration. We will also include catalogs without solid classification to increase our photometry completeness. We have a student that is working on SED fitting over the entire catalog to get the AGN and host galaxy physical properties. I'm also planning to build a multiband and bolometric luminosity function using the entire database at all the wavelengths. There is also a student working on a misclassification project, and we are collaborating with Yale University to get morphological classification of the host galaxy, and we are computing as many black hole masses as we can. So these are my summary and conclusions. So I showed you how it looks like we need more obscured AGN than those previously observed to reproduce the cosmic X-ray background. In STRIPE-82X in particular, we found hints that the ANANA 19 model works better than the others, meaning that there may be a higher discrepancy since it predicts higher number of obscure sources compared to the other models. And to solve this discrepancy, we decided to sample larger volume of the universe. So we are trying with the STRIPE-82XL and with our AGN database. And let me conclude by saying that big data repositories like AGNDB and wide area multiband surveys really open a wide range of new opportunities. So it's not only about obscure AGN fractions, but it's also about multiband luminosity functions, host galaxy properties, black hole masses, mixed classifications, and really everything you can have in mind. Thank you for the attention, and I'm happy to take any question.
Thanks so much for a great talk. We
Thank
do
you.
have time for a question or two. You can unmute yourself or write it in the chat. Either way.
So I have a question, Alessandro.
Mm-hmm.
So what energy bands did you impose upon the Stripe 82? Did you put it in energy bins, or you did it mostly in redshift, right? And so you included, what was the energy band?
So in STRIPE-82X, we use the 0.5 to 10 keV band. So this is true for XMM, and we extended by assuming a power load the 0.5 to 7 keV band of Chandra.
Okay. So in this AGNDB, you're saying you're doing the X-ray analysis, but obviously you can only do it on the stuff that has X-ray data. How many percent of that does have X-ray data? You said you included all every catalog you have. How much does have X-ray data?
Yeah, so we have almost 1 million of X-ray AGNs. Of course, many of them have very low photon statistics, so we are not going to include all of them in the X-ray spectral analysis just because it's not reliable to fit everything. But this requires, so we are not going to set a threshold on the number of counts. I mean, we are going to, but it's not going to be a static threshold. So we are going to perform some simulations to get the minimum number of X-ray photons that we can use for a meaningful fit. So I would say that less than 1 million, because we have 1 million in total, and then we have to make a cut in photons.
Hey, thank you.
You have another question?
I have a quick question.
Please go ahead.
Okay. Hi, Alessandro. That was really lovely and great to see all the progress on this project. I think I just missed it because it went by really fast in the beginning. You showed that plot. I think it was X-ray luminosity versus redshift and the region that you were interested in exploring with the sort of unknown. Can you say a little bit more about sort of how you define obscured within that context? You started out by giving us sort of a background on Compton thick, but I suspect most of these things are not necessarily Compton thick. So I just wanted to hear more about the the nature of the obscuration, the column density distribution, things like that.
Mhm. Yeah, so we defined obscured AGN, AGNs with a column density larger than 10 to the 22.
Okay.
This is, this is what you usually found in the literature, but it's not a static threshold. But let's say that in Striped 2X, we have enough data to constrain pretty well the Compton-Tin fraction. So we are talking about absorbing column density between 10 to the 22 to 10 to the 24. We have, let's say, only 2 solid Compton-Tin AGN, classified AGN, plus some upper limits. So this is why we are expanding the catalog, because we really hope to find more Compton-Tin AGNs so we can constrain better the evolution of them.
So these trends that you're seeing, that you're inferring, right? I mean, you're not seeing sources, you're sort of saying they exist because of the statistical analysis that you perform. And the fact that you're seeing them increase as you go to higher redshift, you're talking about these 10 to the 22 to 10 to the 24 kind of column density sources.
Yes, so the plot that I showed is about Compton-Tin, so up to 10 to the 24.
Okay, thank you.
We have some expectations, some hints also about the Compton-Tin sources, but we are waiting for the new results because the error bars are just too large.
Sure, and this is based on things like hardness ratios, right?
No, so yeah, so our predictions that we didn't publish yet are based on hardness ratio, because otherwise we have only 2 Compton-Tin sources, because we made a cut in X-ray photons. But yeah, we can do it with hardness ratios, but that's going to be not so reliable, I would say. I mean, maybe it's reliable,
do your
but
best.
no, yes.
Okay, thank you. That was really helpful. Appreciate it.
You're
Great
welcome.
job.
Thank you.
Thank you so much. I would just like to thank all 3 of our speakers today for really wonderful talks, and to thank everyone for joining. We are always looking for new speakers for the Frontier seminars. So if you would like to give a talk, or you know a student or a postdoc that would like to give a talk, please reach out to us, or you can go to the Frontier seminar page. There's a link that you can click on to propose a talk. And we hope to see you soon again. Thank you.
Thank you, everyone.
Thank you.
Thanks, bye.
Bye, thank you.